so hopefully there should be something of interest to some of you at least. So yeah, so the topic is textile colorimetry in color management, and the what I'm going to talk about is some very brief introduction to textile color management, and then some particular problems around first of all the colorimetry we use, which is different in what you normally use in textiles. Then some of the solutions to that, including chromatic adaptation and material equivalence. I'm going to talk about the problem of partial adaptation, which of course we know how to do in chromatic adaptation transform, but isn't so straightforward in iccMAX color management. And then also look a little bit about how we can go beyond just using the first generation of iccMAX color management. So this becomes interesting because, of course, as we know, we're seeing much more digital printing of textiles as opposed to more traditional methods of both dyeing and also other kinds of print like screen and block and so on. And this has been rapidly growing for quite some time. One reason is that it's cheaper than traditional methods for small quantities, much faster turnaround from design to print, very suited to personalization, so we can easily do one-offs or short runs, which just wouldn't have been cost effective previously. So that becomes a growing market. And then, of course, to those of us working in colour, the issue of the colour gamut is also interesting, because now we're using some of the currents that are available on the digital printers. We can achieve very large colour gamuts, but not only that, we can actually address all the colours within the colour gamut as well. So that means that we're able to have a full 24-bit color system, for example. So now we have some interesting possibilities, but then also some issues might arise. So we know that textile printing mostly uses large format roll-fed printers, mainly inkjet and with also some dye sublimation. So in the picture you can see a multi-head digital printer using inkjet. So we use color management because it allows us to have some kind of source color and then be able to achieve a match to that on the output. So we can exchange color consistently, and so for example we could get a match between different textiles. We can get a match from our screen design to the final output and so on. And as I think most people will know, the profile is going to be built from a set of measurements. So we make that from the essentially some samples of the medium encoding, most often CMYK or RGB. And those are printed in the form of a test chart. We measure those usually with a spectrophotometer, and then from that we can actually build the profile. Just a note here, when I say CMYK and RGB, of course, in the previous slide, the printer I showed you was actually using more than the 4 channels for a CMYK, and of course, if I have a printer which takes RGB data, it's not printing RGB. It's printing with some other set of colorants. And so we also have this issue that, well, how does the drive data, CMYK or RGB, get converted into current amounts? And whereas we can handle that in color management, in practice that's quite complex, and tends to depend on very specific firmware and so on. So it's more common to drive the device in one of these 2 color spaces, CMYK and RGB, and then the printer driver then handles the conversion into the actual current amounts. So a very common one is where you have, for example, light cyan, light magenta to give you a 6 color set, Another one is where we add orange, green and violet to make a 7-colour set. So as I say, whereas we can handle that in colour management, the normal practice is that we just simply colour manage the CMYK and RGB, and then we assume that the next step is a black box, which is at least consistent. So if we've got the conversion correct from the CMYK, we can expect to get it to work right down the line. Okay, so that's a brief introduction then to what textile colour management is. And then if we look at the overall workflow for colour management, we have a profile connection space. So this is really the heart of colour management, is that we're exchanging via a virtual colour space which acts as an intermediate. And so that means that instead of having to convert from screen to printer, from printer to printer, and have a many-to-many problem, we now have a one-to-many problem where we simply convert each device through its profile into the connection space. So of a single connection space, and that allows us to connect between any pair of devices. So that's the basis of IC.1 colour management. I say IC.1 because we also have IC.2, and I'll mention that later. So this transform is a kind of blind exchange, because the source profile is made independently of the destination. So if the source is, for example, is your display, of course your display profile doesn't know what printers you're going to use, so it can't do a end-to-end transform. So it just converts into the PCS. And so because of that, the PCS has to be very unambiguously defined in a way that's always consistent, so that once we're in the PCS, we always know exactly what that data is. And the PCS is based on CI colorimetry. We can have two forms. One is XYZ and the other is CLAB, but they're of course straightforward to convert between the two without any data loss. So it doesn't matter from a colour measure point of view which of those we choose. So the choices that were made for ICC right back in the 1990s, and this really reflects the graphic arts background of colour management. So we have D50 illuminant and the 1931 observer, often known as a 2-degree observer. And as well as that, because we know in practice that what people want to do roughly 98–99% of the time is to match the media white from the source to the destination. So for example, your display is probably a little bit bluish by comparison with your printed textile. But if you were to actually match the bluish colour on the textile, it would look pretty horrible, it would look wrong. And so instead of doing that, we simply scale everything into the common white point, so that we guarantee that we match the white to white. And we do that by what's called media relative colorimetry. And we store the medium white XYZ as it was measured in the profile, so that we can actually undo that scaling. So if someone does, for some peculiar reason, want to match that bluishness of the display on the textile, it's possible to do that. Okay, so this is the scaling we do. Is very simple, but note, of course, it does mean that X, Y, and Z are being scaled slightly differently. So it's not the same as a linear scaling on X, Y, Z. We're just using the D50 values on top, media white below, etc. So Teams seems to have interrupted. Just getting back. Okay. Yeah, so that's media relative colorimetry. Now, So then in textiles, here are some of the things I think which...
We cannot see your slide anymore.
Oh, sorry, yeah. Teams just suddenly threw a wobbly. So let me go back into that.
Now we can see your screen.
You can? Okay, good, good.
But we just cannot see your slide.
Right, okay.
Guys, if...
Is that working now?
Yeah, it's working now.
Okay, good. Yep. This is my least favorite app for doing these presentations. Yeah, so issues in textile color management then. Of course, we've got to make measurements, and it's very common for textile materials to be partially translucent. And so what we put at the backing of the material does affect the measurement. So this is a slide from Marcus Barbieri's presentation a few years ago at the ICC Expert Day. And you can see the difference that it makes to have different backing colours. We have a second problem, which is that it's very common for white textile fabrics to be optically brightened. And of course, that will affect the measurement. And in particular, the measurement illumination, the one that's used in the spectrophotometer, will differentially excite the OBAs. And then the third problem, which is really the kind of the big problem I want to look at today, is that in textiles, you tend not to use D50 and 2 degrees. You use D65 illuminant and the 1964 or 10 degree observer. So those are three problems. So what does the ICC say you should do? Well, first of all, it recommends that you always use the white backing for the measurement. And this was a change that was introduced, I don't know, probably about 10, 15 years ago. And it was just simply based on the fact that the old standard using a black backing, people found they preferred the results they got using the white. So it's not really necessarily scientifically well founded, but this is the practice that people prefer in the industry. Now, the second thing, optical brightening agents. This is can be a slightly complicated topic, and we haven't got time to go thoroughly into this today. But the basic recommendations are to do one or two things. So one is to use what's known as measurement condition M1 if you are matching the viewing condition and the measurement. So if you get the same amount of UV, then use that. So that way you know that the way you've measured corresponds to the way the thing is being seen. And otherwise, which I think is probably more common for textiles, is that you exclude the UV from the measurement source, and that corresponds to condition M2. So that's a sort of safer bet if you don't think you can actually match the at least the approval condition, viewing condition, with the measurement. And then the third question then is this business of the illuminant and observer, and the recommendation is to transform that to D52 degrees. And so now, of course, you're probably wondering, well, how are you supposed to do that? And that is the $64 million question. So if you could make sure you've got the money ready by the end of the talk, please. So that's our key question to look at, and that's what we want to know the answer to. So we know how to do chromatic adaptation. That allows us to predict the effect of a change in illuminant, but there's no comparable transform for a change in observer. And so that's something we want to look at now. All right, so let me take a look first of all at chromatic adaptation. So this predicts a corresponding colour when a stimulus that you've seen in one adapting condition is then viewed in a different adapting condition. And I've tried to kind of simulate this a bit with this figure from a book I did some years ago. And you can see that it's a picture of a girl on a horse. You have a kind of neutral grey background, and the girl's clothes appear to be a sort of reddish colour, and that's in fact an illusion, because the colour is a grey, which is very similar to the grey background. But because we interpret this as if the scene was lit by a cyan sort of illumination, because it's a cyan and black duotone, what we do is we adjust for the colour of the light. We take out that cyan, and if we take out cyan from grey, of course we end up with red. So that's really what corresponding colour in this case is, and it's the mechanism by which the visual system achieves colour constancy, and we can estimate the effect of it by a transform in cone space. And there are a number of different chromatic adaptation transforms that will do that. So diagrammatically then, if I've got a neutral XYZ and I've got an equi-energy adapting illuminant, so now I should see a neutral. And now I then show the same XYZ, but using a different adapting illuminant. So now that same XYZ now looks, in this case, you can see reddish. It goes the opposite way to the colour, and that's really a representation of what you saw in the previous slide. So the task of the chromatic adaptation is to transform x1, y1, z1 into x2, y2, z2, so that the neutral now still is a visual match under the different illumination. So that's what we're trying to do. So without going into detail of the actual cats themselves, the ICC recommendation is to use the linear Bradford transform to convert to and from D50. So I've got anything else, illuminate A, D50, F11, whatever I've got, I simply convert it using linear Bradford, so that I end up with D50 data. And I also, when I've found my linear Bradford matrix to do the conversion, I store that as a tag in the profile. And for the case which is the most common, for D65 to D50, there is a recommended matrix that's actually posted as a ICC technical note, which you can find. So this is documented in Annex E. This was actually updated. I rewrote this in the revision of the specification, which we published this year, and this is actually currently going through the ISO process as well, so should end up as being an ISO document. So what this does is to take the Bradford transform. This is actually, by the way, based on the CCAM 97S. There's no exponent, so you get the equivalent results without the exponent. But by assuming that D is 1, you end up with a series of 3x3 matrices. And that means that you can then concatenate those. And so you end up, to go from any source XYZ into destination, you just need one matrix, because you've actually pre-multiplied all your intermediate matrices. And this has another very important property, which is that if I have a CHAD matrix going from source to PCS, and then on the other side I simply invert the matrix, I end up with the exact same data. And so that means then that this idea of the virtual color space is realized for any colorimetry, because it means that I'm applying the matrix inverse, and I end up with the same data as I started with if I want to go from a source of D65 to a destination of D65. So, yeah, as shown on this figure here as well, if we start with D65, we end up with the exact same thing, D65 at the end. And I want to emphasize this because it's something which I think many people don't appreciate. They assume there must be some error involved. The only error really comes just from the data precision that we're using. So as long as we're doing it at adequate precision, which in effect means single precision, 16 bits, so then we're not going to see any errors that we're going to care about. So this is the underlying recommendation for ICC color management, and it does mean then that not only can I go back out again to D65, but I can go to anything else as well. So I can go to illuminant A, I can go to F11, I can go to any other colorimetry that I want to. I can actually define a one-off spectral power distribution for all the actual viewing illumination, and I can put that in, and any of those are possible. So this means that I have a single fixed virtual color space for exchange purposes. It's not intended that you necessarily want to use the D50 PCS as your endpoint. It's not your destination. It's just simply the exchange space. Yeah. So as I say, there's no penalty in doing it that way rather than doing it directly. So I could go D65 straight to D65, in other words, a null transform, but at the precision I care about, I'm not going to see any difference. Now, so that's the idea of using it as an exchange and the inversion and so on. But what about when we want to use it for actual corresponding color? So when I looked at this, I realized that very little testing had really been done. So there's a CIC paper by Graham Finlayson and Sabine Sustrunk 22 years ago, and they showed it worked fairly well. And of course, because it's chromatic adaptation, we're talking about perception, and so the only way in which we can test it is by comparing with corresponding color data sets. So the combined corresponding color data set that Ronnie Luo set up some time ago, and also used in the publication for CAM16, Lee et al. That's the one that's been most recently most often used to test chromatic adaptation and appearance models. Out of that data set, there's only one, which is one of the Lucci sets, which corresponds to D50 from D65. So there's not a lot of data to test it against. But when I did that, I found that, to my surprise, that linear Bradford actually is slightly better than all the other ones tested by Lee in the CAM16 paper. So his results then, this is on all the corresponding color data in the whole of the CCDS. So not just D50, but other ones as well. And what you can see then is that these differences are not significant. So I wouldn't argue that Bradford is better than CAT16 just on the basis of this data, but it's certainly not worse. And the other interesting thing was that the difference from the Bradford to the linear Bradford was actually very small, and the differences appear only really in the Z value because you've taken off the exponent from the original Bradford transform. But otherwise, it's a pretty good match. So so in other words, we strongly believe that not only is linear Bradford good in terms of its performance in ICC color management, if what you want is a corresponding color adaptation transform, then it does a pretty good job. that you can't. It's difficult to argue that there's another cat which is going to give you better results. However, let's explore this a bit further, because as I mentioned previously, what a chromatic adaptation transform does is to address the use case that we saw the colour under one illuminant and we want to match the appearance under a different adapting illuminant. So that's what we mean by a corresponding colour match. And so that's one case, but in practice, the way that this is used more often is to take some colorimetry for which I have got, I used one illuminant to do the XYZ, and I then want to get the XYZ for a different illuminant. But there's a kind of a logical approach to that, really, because what I'm doing there is to choose the wrong illuminant in the first place. So really what I should have done is always to use the intended destination viewing illuminant, not something else as an intermediate. So I'm inevitably going to introduce an error if I use that cat approach. So in other words, if I want D50, I should measure D50, or I should calculate D50 in the first place from the reflectances. And of course, that also implies that if I've got the reflectances, then of course I just do that calculation directly. But the problem that we're looking at here really is that very often people don't store the reflectances. What they store, and of course we don't use it in ICT.1 color management, is we don't have the reflectances in the workflow. So what we really want then is to discard the idea of the corresponding color and think in terms of the transforming to our best estimate of the colorimetry as if it was computed from the original reflectance. So that's known as a material equivalence or a material adjustment transform. It's not the same thing as chromatic adaptation. So that's a very important distinction I want to make. So now I'm starting off with some XYZ, and I use a material adjustment transform, a MAT, rather than a CAT to convert into the PCS. So a couple of slides from Max Derhack. So what the CAT does is allow us, the human observer, to say that the colour that they have seen under two adapting conditions is a match. Whereas a material adjustment transform says that these have got the same colorimetry as if I had used that destination source from the beginning. So it's a very similar thing, and the distinction is perhaps a little bit arcane, but nevertheless they are different, and I'll show you an example of how they're different. Okay. So the way we can approach that is using a method that Max Derhack developed, which is called Waypoint normalization. So it's a series of steps that start off with rotation and the scaling and the shearing and so on. And so we end up with a series of matrices in cone space that allow us to calculate this waypoint intermediate, and then we invert that process to derive the output value that we want to. And so Derhack and Burns' very nice paper in Color Research and Application in 2015 that I recommend. So here's an example of doing that. We've got we create this series of matrices, and so this is a kind of a normalization matrix, and you can see then that I've got on the bottom I've got a inverse D50 to A, I've got an A to something else, and I've also got observer differences as well. And so now my final matrix, my final matrix is illuminate A 10 degrees to a D50 2 degrees. So the big advantage of using the waypoint approach is that it doesn't really matter what kind of difference we're looking at, whether it's illuminant or whether it's observed or even whether it's something else, is that we can still get the best fit for that data using this normalization approach. So in this case, then I've got a matrix which is the result of applying these two intermediate matrices together to get me the A10 to D52. ICC has developed a recommendation for doing that for D65 and 10 degrees. It's in white paper 55, available on the ICC website. And then you can see that the matrix itself is actually there on the slide. So that's the one from the white paper. So if I want to test it, then I can start with my spectra, apply the 10 degree and D65. That I then apply the adjustment matrix. I then got D52 degrees. I make my profile in the usual way. And now what my final profile will do is actually to give me an output, which is D6510. So even though when I'm using the profile, the intermediate color space is D52, but my output will be D6510. And this is completely consistent and conforms with the ICC specification. This is what is really fundamental to the architecture. And this was we tested some different methods of doing the material equivalence in a paper in 2018, and so this figure here is looking at Munsell glossy. These are the high chroma colors, and as you can see, we've got Cat02, Cat16, the linear ICC Bradford, and also the Waypoint. So the original is the black line. The ones I calculate into D65 directly from the reflectance, so that would be my material equivalent value, is the red line. And you can see that the chromatic adaptation transform predictions mostly are somewhere in between the two. So they're not quite achieving the ideal is to achieve the red line. These were the reflectances that we tested in that paper. So you can see we use these Munsell glossy, which is the ones that Max used to train the waypoint normalization in the first place. And we also use the in situ reflectances from ISO 17321. So it's a smaller set, but it's perhaps more representative of real world colors as opposed to things like colorants and so on. And then looking at the results from that, then you can see that the Cat02 and Cat16 performed the worst on both data sets. Waypoint did best on Munsell, which is not surprising given it was trained on Munsell, but linear Bradford was similar, maybe slightly better in terms of the D50 on the ISO 17321 data. And by the way, for Cat02 and Cat16, we applied the recommendation of the two-stage transform via illuminant E, and we didn't do that for Bradford and Waypoint because that's not part of the transform. So we used the recommended method, although because of course we're using a full degree of adaptation, what you can see from the results there is that it actually makes no difference if you go via illuminant A or not. So that two-stage approach is applicable when you have some degree of adaptation involved. But if you're dealing with full adaptation, then it's not going to help you at all. Okay, so you might think, well, that's all a bit complicated, so why should we even bother? And there are people who would argue that we just connect, we'll ignore the ICC PCS and we'll just have a D65 10-degree connection space, and that will avoid all that trouble of converting the colorimetry when we make the profile. If you recall from that workflow, you start off with the measurement data, you've got the D65, and then what you've got to do is to apply the matrix to get the 52 degree, and then make the profile from that. So you can avoid all that. And of course, if you think there are these theoretical conversion errors you're going to get, then you're going to avoid those. But the key thing to bear in mind there is that that approach is only ever valid in a closed loop workflow. You can't take a profile which converts into some arbitrary PCS and then just connect it to any other color, any other profile, because it's not going to work. The PCSs will be different, and you'll get really big mismatches. So it's an approach you could use in a closed loop. It's not an ICC workflow. It's not interoperable. The whole point of ICC workflows is meant to be interoperable. And as we've shown, the conversion errors for D6510 back to D6510 are negligible, and they're just limited to the data precision and also any transform model error, which is completely separate from the illuminant. So because there's still people who don't quite get this, so we did some testing on this just to show. So we started with 2 textile printers. So we've got a HP Latex 560 and a Durst Row 512R. So the gamuts of the 2 printers you can see in the figure, and we calculated the gamut volume. Not that we needed it, but just because it's fun to do. This was some work we did in recently in ISO to develop ISO 18611, which is about comparing color gamuts, and CIE publication 246, which is about describing color gamuts. And so we're able to triangulate the gamuts and then calculate the volume from the triangulation. So these are the 2 printers that we tested, and then these are the results. The paper is Nussbaum, Kresovich and Green from EI earlier this year, and you can see that the methods actually are differences are trivially small. So these differences really are just the modelling error, and whereas the argument is that you should get better results with the non-ICC PCS if you're doing a D65 to D65. Actually, it doesn't hold, because in this data we see that the results are not significantly different, and there's certainly no advantage in using the non-ICC approach. So if you're worried about whether that white paper 55 method is going to work for you or not, you can see from this that it absolutely is fine, and there's no advantage in doing anything different. So we're confident this is the right approach to use. But now, what about if we did want to get a better result in terms of the material equivalent prediction? So we talked about using chromatic adaptation transforms, but of course these are derived from corresponding color data sets. They're based on visual observations. Waypoint is also based on training data, but the visual observations which are used to derive the CATs obviously contain a lot of observer noise, and they're not exactly predicting material equivalence as well. So if we were to calculate it from the reflectance, it wouldn't be subject to noise. So that's what I suggested in the beginning, that what we'd ideally do, if we want to end up with D52 degrees, we should actually do that right from the beginning, and we calculate that from the reflectances. But the reason why people do it, because they don't have the reflectances, and so then the question really is, well, can we actually find the reflectances in such a way that we can then predict under a different illuminant and observer? And the answer is yes, and we can do that by spectral reconstruction. And my student Tanzima Habib has done a couple of very nice papers on that. So she, as part of some work in ISO, she evaluated a whole series of different spectral reconstruction methods. You can see the list here. They all actually do reasonably well. In fact, some there's nothing that really goes wildly wrong. And what she found, looking at the very large number of data sets, this was a really exhaustive and probably quite exhausting set of tests that she did. And she found that across all the data sets, you could see clearly that the two methods that performed well were the weighted pseudo-inverse and the third order polynomial regression. And one was slightly better if the training data was similar to the test data, and one was slightly better when it was different. But overall, both of them gave a good performance. But one thing we've learned from implementing those is that the polynomial is a lot easier to implement, and we were able to make an iccMAX profile so that we now have a profile which does the conversion from XYZ into reflectance. I think it's for, I can't actually remember what the illuminant is for that particular profile, but nevertheless, it means that we have a profile. If you want to convert XYZ into reflectance, you can actually just do it in iccMAX. So this seems to me a much more logical approach to doing material equivalence, where I want to know what the XYZ would have been had I used a different illuminant from the one I actually did. And to implement the polynomial, I just simply calculate the set of coefficients. I do a third order expansion on the data set. So I've got S as my set of training reflectances, D is my expansion of the XYZs, and I simply multiply the two together. And so this is a pretty simple method to implement. So I did a preliminary test on this for something I was writing at the moment, and I compared it with the results that we'd previously got for Mumcell and ISO 17321 using the same transforms. And what you can see from that is that the reconstruction method is significantly better for all cases. So that means that we're fairly confident that this is a better approach even than the Waypoint. So Waypoint was better than in general than the CATs. Bradford was better than the CAT02 and CAT16, but the reconstruction gives us really much smaller errors. You can see if I compare for illuminant A going to D50, I've got errors on the order of 4 delta E in those two illuminants, but in those two CATs. But with the reconstruction method, I've got an error less than 1. So that really is a big improvement, and that's just simply implementing that third order polynomial. So this is something Tanzima is working on at the moment, and she will be doing as a paper in the near future. So that's a little bit then about chromatic adaptation, when we should and when we shouldn't be using it, and how to get those estimates. So then next thing I'd like to look at then is this idea of complete versus incomplete adaptation. So you might recall that when we said we can do this linear Bradford as long as we assume that the degree of adaptation is always 1, and that essentially implies that if I'm looking at a display I'm completely adapted to the display white point. And when I'm looking at a surface colour, I'm completely adapted to a perfect reflecting diffuser under that the illuminant that I'm using for that viewing condition. And there's no partial adaptation. But of course, in practice, we know that actually lots and lots of papers have shown really well that the real adaptation state is never complete. There's always, unless we have very, very high luminances, but in most cases it's going to be incomplete. And we have a sort of a subcase of that where it's quite common to print on coloured materials, and although I know some people argue it's not really chromatic adaptation, but you can show that it's the same effect and you can model it in exactly the same way. So the Financial Times that's shown in the illustration there, it's quite common that people think when they see the white point of an image that they're looking at a white which is actually whiter than the substrate is, because they've adapted to the white to the pink substrate, and then they interpret that that absence of colour as if it was a white. So there is this partial adaptation that takes place. And Greg, who I believe might even be on this call, has done quite a lot of work on that, and he's I think shown some conditions under which that takes place. And previous work we've done also suggested that you could model that as being roughly 2/3 complete adaptation. So now the big problem in IC.1 is that we don't have a way of doing incomplete adaptation in the architecture. In IC.2 we do, because we can actually choose the transforms and we can really do whatever we want there. We can also do spectral connection as well as colorimetric connection. So it is possible then to do something in IC.2, but my question really is, what do I do about IC.1? Those of you who've already started using IC.2, you'll see that there's an IC technical note which was published last year on how to do that in the CMM. So not necessarily in the profile, but you can do it in the color matching method, which connects the two profiles. But we know that IC.2 is not yet very widely implemented. You can't do it in Photoshop, for example. And so I wanted to see if we could come up with a way of doing it in IC.1. So some points we need to take into account then is particularly is that the rule in the specification about the rendering intents is that the colorimetric intents must be measurement based, so they can't be adjusted for things like viewing conditions. So in principle then we should not do these kind of incomplete adaptation adjustments in the colorimetric rendering intents, but we can use the perceptual intent. So just to very quickly then go through some examples. So, and I want you to try to imagine the adapting effect of the pink background. If I've got a neutral and a white, and then when I put that onto a pink background and I partially adapt to the pink, then the greys look slightly bluer, and perhaps best seen in the lightest colour. It looks a little bit bluer than the one on the white background. So that's what I would like to try to model using an incomplete adaptation approach. If I use a full adaptation, effectively I'm using the media relative colorimetry, then I get this, which probably looks even worse. But we can probably, from those two examples, see that what we'd really like to do is something in between. In other words, an incomplete adaptation. So actually a very simple way of doing this then is to start with my source illuminant, and it can even be D50 or it could be something else. And then I calculate an adapted white using a chromatic adaptation transform, which incorporates a degree of adaptation factor. I can use Cat02, Cat16, I can use anything else, and I can use a two-step cat if I want to as well. But what I get from that then is the my intended adapted white point, and so then I use that as a source white in linear Bradford, and I then use that then to calculate my chromatic adaptation transform to go into D50 PCS colorimetry, and I build my profile from that. And the that lookup table then goes into the perceptual rendering intent. I make my immediate relative intent in exactly the same way. And this was described in a paper I did at the ACA conference a month or so ago. So just then to take a look at some results then. So this is using, I think this was a 50% degree of adaptation. And you can see that it partially adapts for the background color of the pink. And then comparing that again with the more bluish appearance with no adjustment, and then the kind of full adaptation approach, to my mind, it looks an improvement on both of those. So that was the goal of that work. So then to wrap up then, I want to just, I've touched very briefly on ic.2, which we also call iccMAX. This has been around as an ISO public specification since 2019. And the main thing it's intended to do is to provide solutions where you don't want to use the D50 PCS. So you can have a custom colorimetric PCS with any observer and illuminant. You can also connect spectral data with any range and interval, as long as they're a reasonable range within the visible spectrum. You have these custom to standard conversions, so that, in other words, you have a default of the D52 PCS, so that if you want to try to connect two profiles with different custom PCSs, they can't be connected because they're different, and so what happens is that you use the default standard PCS instead. You can do conversions using a whole range of flexible kind of transforms. So whereas you could, in using linear Bradford, do it as a 3x3 matrix, but if you wanted to do something much more complicated, you want to implement Cat16, for example, you can certainly do that. And you can implement a Cat or Mat kind of transform. So many other features in ic.2. In order to help people with implementing it, we've made available a very comprehensive set of source code, test suite, example profiles, and also some compiled binaries. So it means you can actually dive right in and start working with command line binaries and do some of the transforms that we've talked about. So that's all on color.org if you're interested. So what iccMAX does then is include these things called multi-process elements. So whereas the traditional ic.1 has a fixed sequence of transform elements of curves, matrix, and lookup tables, so now in iccMAX you can actually use any number of these elements in any sequence. So you can have one-dimensional lookup tables. You can have matrices of any size. You can have multi-dimensional lookup tables which are not restricted in the number of channels that they have, unlike ic.1. You have a very powerful calculator element, which is essentially a programming language, especially designed for this purpose. You have the spectral colorimetric. You have something called tint curves. and there's also a color appearance model as well. So all these things then give you much more flexibility to build any kind of transform that you would like, rather than be restricted by the IC.1 available transforms. So so this is the kind of thing we did in the paper where we looked at comparing the different CATs and MATs. So we used the PCC, the profile connection conditions, to provide the illuminant, the observer, the viewing conditions, and also the custom transforms. So that means that if we look in the PCC, we can see that we've got, let's say, D65 illuminant, we've got a particular observer, and so on. And one of the nice things about the architecture then is that whereas the profile contains one PCC, at runtime I can actually ask for a different PCC. So that means that if I've got a profile which has got spectral data, it's got a given colorimetry intention in the PCC, I can say, well, no, I don't want that, I want something else. And I can do that at runtime by providing the external PCC from another profile. And it also allows me to use environment variables. In other words, at runtime, I can pass in arguments into the calculator element. And I can also pass in things like the actual real viewing environment at runtime as well. So this was the workflow we used in that project. We started off with reflectance. We did the pre-CS transforms, and we produced XYZ output. And then you can see that we're starting with spectral PCS, convert to colorimetry. We provide both the PCC and the custom colorimetric PCS. We apply those to the standard PCS. We end up in the D50 standard one, and then we convert using the standard to custom on the output side, and then we end up with some output values. So so that work was all done inside ICC profiles using the version 2. So, and finally, some conclusions. So I think I've shown that the linear Bradford performs perfectly well for textile colorimetry, whether you want to do chromatic adaptation or whether you want to do material equivalence. And if you're using IC.1, then it's strongly recommended to use that approach. For material equivalence, and also that includes things like where you want to change the observer, which we can't easily do in colorimetry, we use the Waypoint transform, and there is one provided in the IC white paper 55 if you'd like to do that. We've seen that we can do lots of other things with the new color management architecture, iccMAX. That would be another talk really to go into that in more detail. And we've also seen that if I want a material adjustment transform, then spectral reconstruction is the best way to go. And I can actually do that quite straightforwardly in an ICC profile. And then finally, I've shown that the partial adaptation approach could be implemented in IC.1 in the perceptual rendering intent. And you can also do it in IC.2, either using the flexible profile connection conditions, or you can do it externally in the CMM as shown in the technical note. So I think that will do for now. So thank you very much.
Thank you very much, Phil, for your excellent talk. Anybody have any questions to Phil? I think, yeah, it's such fascinating